lecture's louder. Anyway, so as you've noticed, lecture 6 is painful, and lecture 8 is even more, chapter 8 is even more painful because we haven't got experience developing Windows apps. And that's why I haven't given you these quizzes on chapter 8. I'm going to write one for a few weeks in the future to encourage you to go over the slides. We're only going to cover about half of what's in the book. And we're going to replace some of that material with newer material because the book is a little too tough. It is the Bible for this topic, so it's worth looking at, but it's, I can't follow it in detail in chapter 8. And I just want to, so anyway, what I do want to do is learn how to do some of these attacks and really do some attacks hands-on. That, I think, is the most productive use of our time. And you don't need to understand everything to do the attacks. There's quite a few things to learn. So here's my plan. I don't even have iClickers today. I've got a brief lecture to finish what more I'm going to copy of chapter 8, and then I have a demonstration of Project 15, which I have been working on for the last 3 days because it used to be on Windows 7, and now I got on a server 2008, which wasn't that hard, but I made some attempts to clean it up. I used to be 2 projects, and now it's just one very long project. So don't start this the day it's due. You won't be happy. This is a long one. But I think that shows you how to actually do it. And as with almost everything in hacking, the theory is more complicated than the practice. So let's see if we make any sense out of this stuff. I'm going to break it into 2 lectures, one for the theory from the book, and the other for how to do it hands-on, which we'll do, and that's how I find it best. I welcome comments. But you're quite correct. That chapter is unusually daunting. It appears to be the case that the author actually assumes that we have developed Windows apps and we know how to do it, like a real developer. And I don't, so I'm never going to get it up to the level of what he's stating here. We'll go through it a couple semesters in a row and get a little more of it. But I'm certainly not getting it all. But anyway, in the world of security, it is often enough to get a CISSP type management comprehension where you know what the basic problem is, what the threat is, and the most popular way to fix it. Not that you know every little detail, but you have some clue what's going on. And that might be the only level at which you get some of this. But anyway, so we're overflowed the stack on Linux. We've done quite a bit of that. And you can overflow the stack on Windows, although Windows is much more complicated. In modern versions of Windows, there are a lot of defenses. Like I've said many times, Windows is more heavily defended than any other operating system I'm aware of because it's been under attack so long, and Microsoft stopped pretending that didn't matter all the way back in 2002 and has seriously been trying to protect themselves from all these attacks. So now, if you compile any new app, this flag is turned on by default to protect the stack. And the first thing it does is put canaries on stack. That Microsoft calls them security cookies. This is the same thing Ubuntu Linux does, and everybody's done for quite a long time. So what this does is it puts a value here where the yellow thing is. So every time you make a stack frame, because you've entered a subroutine, you save your local variables, then you put the cookie value here, then you have the saved base pointer return address on the other side of that cookie. So if somebody overflows a variable like name and tries to change the EIP or something, they can't do it without altering that cookie. Now this means the cookie better be somehow random and unpredictable and hard to find, and as we'll see, nothing's ever perfect. But it does make some attempt to do those things. What Microsoft does is it tries to make it random. So it XORs a whole bunch of things together, including the date and time and the process ID and the thread ID and the tick count. And this, by the way, I recognize as something Dan Kaminsky recommended at DEF CON about 3 years ago. About 3 years ago, there was a big scandal because a Canadian researcher found that 1 in 1,000 of all the HTTPS certificates in the world had identical public keys shared with each other. If you just try all the supposedly random public keys and try dividing one by the other or do some mathematical trick, you find out that a whole bunch of them are using the same prime numbers. He said, how can that be? And the first thought was, there was one idea is that if someone makes like a bunch of VPNs, they might not generate a different key for each VPN. They could just generate one and then flash the ROM a million times and sell a million VPNs all with the same key, which is kind of sleazy, but that could happen. I am aware of refurbishers in Mexico that actually refurbish NICs and make them all have the same MAC address. And as long as each company only buys one, they don't notice. And that was the first thought. But what further investigation revealed was that this is because the random numbers aren't random. So when you turn on your VPN, it boots up, it runs a routine, it runs the pseudo random number generator. And if you have another one with exactly the same hardware, the same chips, you turn it on, it has a very high chance of getting the same random number. So that's the really tough thing. And what Dan Kaminsky said is if you want to fix this in a hurry, there are purists that say you must pay for a special hardware random number generator, which is now included, I think, in the Pentium i5 or i7, which is just a resistor, and it multiplies the random noise of the atoms up. So that should be pretty random, although I can imagine exotic attacks like putting the computer in magnetic field to affect the atoms or something, but it should be pretty good. But what he said is if you can't do that, what you do is take your computer has several clocks. So combine the results of several clocks running at different speeds, and that will really wave around in a random way. And that's what Microsoft did here. They took this clock in milliseconds and that clock in nanoseconds and the count of CPU cycles and OR them all together, and this should create a number that wavers around pretty randomly. You don't like it? Well, what are you going to do?
Well, exactly. I remember in the way back when John Knuth was talking about this in some numerical algorithms.
Yeah.
It basically says, random numbers, just you don't get them by accident. That's not going to be random.
That's right. It's a huge problem. That's why mathematics and cryptography is really hilarious, because there are like 3 words that you just throw around as if they meant something, like random and trusted. And when do you really trust anything? What makes you think you can trust anything? And in the old Microsoft way of thinking, they say, well, as long as it's like reasonable. You don't imagine some malicious person has got a conspiracy to like trick you with 10 lies. You can't trust it that much, but that's what hackers totally do, is find some evil way of tricking you. Absolutely. And so it's like the root of DNS and the root of HTTPS. I mean, who can you really trust with that kind of responsibility, where they could redirect all the traffic to every bank and government in the world? Who on earth could really handle that responsibility? The answer is probably nobody. Anyway, so that's the game. So Microsoft chose all those things to mix together to make the hopefully random cookie. And if somebody tried, they could try predicting the cookie, and somebody went and checked it and said that even though there's 32 bits long, there are effectively only 17 bits that are unpredictable there. Because all this attempt to make it random only is about half successful. And 17 bits means 2 to the 17 is 100,000. So that means if you just guess and try your attack 100,000 times, you'll be lucky by chance. So you can't win everything, but that's what you get. 5 orders of magnitude improvement in security, if you want to look at it that way. All right. And the way this works now, which I found to be a great relief because I was doing capture the flag contests, and I always saw this stuff at the start and end of every function. So functions that are protected by security cookies start with machine language instructions to create the security cookie and store it someplace at the start of each function, and then put it on the stack. And then when you come back from the stack, it calls this check function, security check cookie, and it will not let you return from the function if the cookie check fails. It will instead give an error message and crash, saying on Ubuntu it says stack smashing detected. And I don't know quite what it says on Windows. I think on Windows it pops up the Microsoft box that says please tell Microsoft about this problem. But anyway, it stops. So here's the check. And what the check does is it compares it to an authoritative value that is stored in the data section of the file. Okay, so anyway, and we'll get there. And then if the check fails, it calls a security handler using a pointer stored in the data section. And of course, as you probably have already guessed, these are the weak spots where it can be attacked. I think the cutest one, we'll go through a few of these, the cutest one is just let the stack fail and overwrite the pointer to the failure message, and then you take control after the failure, which is pretty cute. But that's the problem. I mean, fundamentally, if you can reach and overwrite the RAM, nothing can really stop you. They can just make it more difficult. So here's another thing they did since 2003 and later. Microsoft no longer lets you control the order in which parameters appear on the stack. They used to just appear in the order in which the developer put them in the source code. And they finally wised up and said, all right, we've had enough of this crap. The way it used to be, you would have your name and password up there, and down here you might have important things like whether you're the administrator or not in an integer variable here, so I could overwrite the password and change myself to administrator. And so they said, this is for the birds. From now on, we're going to put arrays always at the bottom. So the arrays can't overflow into other kinds of variables anyway. Now, a name could still overflow into the password, but this makes it harder to do as much damage here. It tries to guess the least harmful order in which to put the parameters, so the ones that overflow are near the bottom. So they'll hopefully just hit the cookie and nothing else. All right. So, but you can overflow the buffer and then wipe out all this stuff. Wipe out this cookie, wipe out the saved EBP, the saved return address. And then above that, you've got the parameters from the previous stack frame that were passed in to the function to be used. So some of those parameters up there might actually be used in the function. And see, here's where under certain conditions, you can destroy the stack cookie and still do your exploit before it tries to return, so it doesn't notice. So here's some examples. You've changed the cookie, but if the parameter is used in a write operation before the end of the subroutine, you can use that to write to memory and take over the machine and never return. And that's why I mentioned before when you're when you're debugging functions, one problem is when you step into the malicious function, the code might never come back because they might be doing something like this. The other thing you can do is find the authoritative cookie and overwrite it. So now you know what it is, so now you'll pass that test. And the other thing I can say, which is awesome, is overwrite the handle that controls the consequence of failing the test, and then just let the test fail. And you still have control. Or you can even just set the handler to 0 so that when it tries to do, it checks the cookie fails, it goes to the cookie fail handler, and it's not go good, so it goes to the exception handler, and you put your exploit there. Those will all work. So, anyway, there's heap-based, and all these are minor variations stepping up. Then there's heap-based buffer overflows. The point of the heap is you've got data that would just waste a lot of time. Like if you have a web server, these requests come in, you handle one request, and then you want to throw it away and use the same memory for the next request. And the requests vary in size. So that's exactly what the heap is for. You have stuff coming in, you don't know how big it is, you don't want to keep it permanently. So you keep on creating blocks on the heap to store it, and then deleting blocks and recollecting that space to use for later data. That's what the heap is naturally doing. And that, of course, makes it quite dangerous. Unlike the Linux programs we've looked at, the Windows programs have a lot of heaps, and there's a pointer stored in the process environment block. You can find it because 30 bytes into the thread, the TEB, I think this is, not PEB, there is a pointer to it. So you get a code from there and then go to the pointer relative to that, and you can find the location of the process heap. It's not a secret. And a lot of the API functions use that. And you can create more heaps in your process as much as you want. They're all inside the default process heap. So it is a complicated structure looking sort of like this. You have the default heap and then a heap count and then a heap list, and you have these other things like the PEB outside there controlling it. As a Microsoft Windows pretty much turns into a mess. It's complicated. But fundamentally, they're all similar structures. And so they allocate with a heap allocate function, which is the same in Windows 16 and Windows 32. And then when they're done with the chunk, they call heap free. And I think the heap grows upward. And we talked about this before. The fundamental weakness is that if you create a object in the middle to store data and then you free it, then it has to take the forward pointer from this node and skip over and make it point to this one, and take the backward pointer from that node and overwrite it with this. And that means if I overflowed this heap and I could change those values, I can control both parts of an arbitrary write. I can control the address you write to and the data you put there, because both of those are controlled by things I can overflow into. And that's just due to the fundamental way a heap works. Any kind of linked list works that way. So that's why it's pretty cool. An overflow in the heap can be exploited most simply when you have a free.
Is that a linked list of heaps?
Yes, heaps are doubly linked lists, forward and back. And that's why if you want to check it, like what Cisco routers do is they have a check heaps function that walks the heap. Goes from here to here to here to here to here to the end, and then I think it also goes back. And if it ends up anywhere other than right where it started, then the heap is damaged, and in Cisco's case, it throws everything away and just reboots. In other cases, it'll have an error message or something. So that's why to maintain any linked list, you have to do these writes, and any overflow will give me an ability to control both halves of a write, which is awesome. It's very easy to take over a machine. One of my students was telling me in the lab the other day, he had found a vulnerability in a system that let him write 1 byte to an arbitrary location, but it had to be 0. And I said, you can't do much with that, and he was totally taking over the thing with that. Now that's a challenge. But this is not a challenge. You can control the address and the data, so you can totally just overwrite a return value or a function pointer or something and take over the machine, and we were doing that in Linux. Anyway, there's a lot more to it. The Microsoft has a whole bunch of crazy additional features to make the heap more efficient, like a look-aside list that has something to do with trying to organize the heap structures so you don't spend all your time shuttling them around to try to defragment the heap and such. But anyway, the general process is the same, and so there's 3 basic ways to do it. You can overwrite the pointer to the exception handler, or to the unhandled exception filter, or a pointer in the process environment block, and all these things are like the structured exception handlers. They're eventually used to control code execution, and you can point the code to where code you want to execute. The process exception block has a variety of functions that are called when you exit a process. And this is something we talked about before. One way to take over the machine is to get the stored instruction pointer that's called when you leave a function, but another way is to get all the things that call when you end an entire program, like destructors for the object and so on. And that's what this stuff does. When the program is done and tries to return to the operating system, it calls certain routines and you can poison them. That's just another way to take it over. Windows 2003 server didn't use those pointers in the process environment block, but they had other pointers that we could control. And the XP went up to something called vectored exception handling, which stores information about the handlers on the heap, and they can be changed with heap overflow. This is a Black Hat Amsterdam talk designed for Windows XP. And they found a way to use set unhandled exception filter to find the pointer. This is fundamentally the problem. Remember how I talked about so many undocumented Microsoft routines are used by programmers because you can just disassemble them and look in there and see what they work and figure them out even without Microsoft documenting them. And people do. If you do overflow stuff in the heap, then you might be able to make an arbitrary write, but you have corrupted the heap. And if anything tries to read things out of the heap later, it's probably going to make your system crash. This was in fact happening to me today for a similar reason, which I'll talk about a little later. But anyway, once you would like to fix the heap. Now, one thing you could do is try to walk the entire heap, figure out what should be there, and put it back in its original state. But what's a whole lot easier is to just run an initialize function to make a fresh empty heap. So at least it's not invalid, even though all the data stored on there is lost. And that might cause you to survive long enough to run your shellcode. If you know sloppy attacks just crash and the process hangs or something, you would like to make it so the user can keep on using their browser and whatever you did didn't damage it, but that's a whole lot more work. Anyway, all right, the exception handler. If you go changing that and you forget to put it back, then a later exception, in fact, indeed, an exception might happen in your shellcode, and then you've got an endless loop where the exception calls the shellcode and the shellcode causes an exception, especially since you may remember shellcode is very rotten stuff. It doesn't have any error handling. So I was sort of baffled when I first used Metasploit shellcode, and if it tries to phone home and the CNC server is not listening, it creates an exception. Every possible little error creates an exception. And I hadn't thought of that because I'm used to professional code that would handle that, but the whole point of shellcode is you discard all the unnecessary stuff like error handling to make it smaller. So then there's these COM objects that we talked about before, these Microsoft code constructs. It's an object, it's got methods and attributes that can be active or just data sitting there, and these things are all created on the heap, and there are an unbelievable number of them, and what a mess there are. Each one of them has a Vtable, which specifies its interfaces, and those are the pointers that those are basically how you enter these things, like pointers. And what's amazing, these things contain data, and these data fields can overflow into other objects. So one COM object can overflow in the next COM object. And I found a IBM talk, the slides from IBM talk talking about this. The average window install has thousands of COM objects. And when Microsoft discovers that one of the COM objects is vulnerable, they typically do not fix it. They just put it in the kill list. And there's a kill list of known dangerous COM objects that is now 600 items long. So there are a ton of vulnerable COM objects, and what this IBM talk was showing is it is very easy to trick the operating system into loading one of the forbidden COMs. So there are 600 vulnerable COMs at known vulns, and you can easily just use them, even though they're supposed to be blocked, because the kill list enforcement is not very good. So that's good, clean fun. There used to be something, it used to be ActiveX objects, they're pretty much gone, and there was a way to mark your ActiveX object as safe, and then it would bypass the security, and it was just a bit you could control. You could just, oh, mine is safe, don't test it. This kind of stuff tends to happen. So they made this thing you can download called a COM viewer. I took a look at it, and holy crap, they're not kidding. You have a lot of these things. And something like 60% of them are known to be vulnerable, and probably the rest they just don't know yet. Anyway, that's good, clean fun. All right, and there's other stuff. Yeah? No. Okay, there's other stuff you can overflow, like the data section itself. So suppose you have a program and you create a buffer and a couple of pointers you're going to use, and you put them outside main. That makes them global variables that are shared by all the routines, and they will be stored directly in the data section. And now, if you have an overflow in the data section, you can overflow these supposedly static variables and change things. And if you change those pointers, then you'll change code execution. So that's good fun. You could overflow the buffers in the thread execution block, changing pointers. This is a theoretical exploit that hasn't been done, but It's an option to think about. So, like I say, there are many, many extensions, but now what I want to do is end this theory talk and just go through an example, which will take a while, of how it turns out in practice. So this is the end of chapter 6, I think? Chapter 8, all right. So this is 127, chapter 8b, all right.